everyone, welcome to the first unit of calculus. In this video we're going to be going through what calculus is and what integration is and the overall picture as to where we're trying to get to, and we're also going to be looking at rates of change, which is the first specific skill that we need to start. So just as a bit of an overview, differential calculus, there's differentiation and integration, and they are kind of the opposites of each other. They undo each other. Like when we had expanding and factorising, you could go back and forth, round and round in circles. And that's what differentiation and integration do to each other. So we're going to spend most of the unit looking at differentiation and then go into integration at the end. But simply put, differentiation is a rate of change. It's the slope. Okay, we looked at slope in linear functions. We looked at, when slope is m and rise over run and all that kind of thing in linear. Now we're going to do it with other functions such as the quadratic here, a cubic, a quartic, all those kind of things. We're going to be looking at how we find the rate of change or the slope in those. Okay, so that's where we're heading. But today we're going to be looking at rates of change because that will lead us into differentiation. So there's 4 different rates of change that we're going to be looking at. They can overlap, some of them. But the first 2 are quite simplistic. The second 2 take a bit of calculating. So let's look at the first one. So constant rate of change. Now this is probably the one that is most familiar to you. So I'm just going to draw a little graph here and we're going to talk about, let's go unit price and total cost. So constant rate of change looks at things that keep their rate constant the entire time. So for example, an hourly rate for a worker, if you're working say at Coles and you get $10 an hour, it goes up by the same amount each time. Okay, so for each hour, you get $10. 1 hour, another $10. You work another hour, you get another $10. Okay, it's constant. Hopefully you're starting to think that there might be another word for what we use for constant. Another idea is litres of petrol. So if we've got the same amount, we buy no petrol, it costs us $0. We buy 1 litre, it costs us $1.40. We buy another litre, another $1.40, and it goes up and up and up. The price of the petrol will never change. Okay, it's constant. So you should have picked up from the graph that constant means linear in what we have seen this year. So it doesn't change. It doesn't get steep and then drop and then go up. It doesn't fluctuate. It's constant. Okay, so where you see the word constant, I want you to think about, could you write a linear equation for that? For example, $1.40 per litre of petrol, we could make the amount of litres equal X. Therefore, Y equals $1.40 times X. Okay, so if you're thinking constant change, you're looking at a linear equation. So on your exercise sheet, the first one is just identifying which ones are constant. For example, the rate of growth of a baby. Do babies grow by the same amount every single day? Probably not. I don't know, not a parent. Rate of growth in Australia's population, would that be linear? So many people per day, same every day, would it be linear? So that's getting you thinking about what kind of situations it would happen in. And the questions down here, you're just identifying, is it constant? Does it grow by the same amount each time? Okay, so that is a constant rate of change. Another one we need to look at is a variable rate of change. So these are ones that change. For example, with that petrol, we might $1.40 per litre, but we have a deal as a business. That means that if we buy more than 100 litres in a day, we get it for, I don't know, $1.10. Okay, so the first 100 litres we'd have a slope of going up by 1.4, and then at 100 litres it wouldn't be quite as steep because the petrol is cheaper. Okay, so we started off with one slope, one gradient, and it changed. And we've done lots of examples with that. If you think, if you think about our quadratics, it's changing the whole time. If you think about our cubics, it's getting steeper, it's flattening out, it's getting lower, it's flattening out, it's getting steeper. Even our logs and our exponentials. Okay, if it's not a constant rate, it's a variable. Okay, so those are your two options. If it's not constant, it's a variable rate. And you can see on some of these examples, every one of them, that you didn't identify as constant will be a variable. Where it starts to get a little bit trickier is with average and instantaneous rates. So average rates, we're looking at a variable rate of change, but we want to find on average what's going on. Okay, so here I've just done a little example. Let's say it's a person, and down the bottom here on the x-axis I have their age. So when they were born, they were pretty short, and at 5 years of age, of 20 years of age, they're getting taller. Obviously this is not to scale or accurate or good in any way, shape or form, but it's the example we're going with. So over here they're 100 centimeters when they were 5, they're 200 centimeters when they're 20, so they're pretty tall, I think. And we're going to find out what their average rate of growth was between ages 5 and ages 20. Okay, and I just want to point your attention here to your formula sheet. So we've got a calculus section down here. Okay, and we want to find the average gradient. Now, the gradient is not on this part, and that is because it's right back up here when we did linear. Okay, so it is on your formula sheet. You've just got to make sure you're using your formula sheet so you know where it is. So gradient up here, m equals y2 minus y1 over x2 minus x1. And we're going to find the average gradient. So I'm just going to make these into very clear points. So our x value is 20, y value is 200, x value is 5, y value is 100. Okay, and if it's been a while since you've done this, we're going 20, 200, and 5, 100, and you're just going to label x1, y1, x2, y2, and sub them in. So 200 minus 100 over 20 minus 5 gives us 100 over 15. So that's 6 2/3. So my gradient is 6.67-ish. Okay, so on average, between the ages of 5 and 20, this person grew 6.67 centimeters per year. Okay, on average. So this is nothing we haven't done before. It's just getting your head around it a little bit. So they will give you 2 points and they'll ask you for the average rate of change between them. Okay, you can see on your exercise sheet, where are we? Down here, they've given you the points and they want you to find the average growth between them. And where it gets tricky is when we have things like quadratics and cubics. But I'll let you have a go at them and see what happens there. Now, instantaneous rates of change is the fundamental part of differential calculus. So if you're unsure of anything that I've talked about so far, pause it, go and do those exercises first, get really, really comfortable with everything else, and then come to instantaneous rates of change, okay? Because we're going to be going through quite a bit in this part. So instantaneous rates of change. If we're looking at, let's say, a cubic function, we already know a little bit about changes. So we can see here that our gradient is positive, it's growing. We looked at when our turning points or our stationary point of inflection, we were looking at it was flat. It wasn't growing, it wasn't decreasing, it was just flat. Down here, we're decreasing, flat, increasing. So we've seen a little bit of gradient. Now, what we looked at on the last slide, we're looking at, say, an average rate of change between those 2 points. With instantaneous, we want to find out, say, what the rate of change is right there. Okay, how fast is it growing at that specific point? How fast is it decaying at that specific point? Okay, and we do that using something called a tangent line. So a tangent line is a line that touches only at that specific point that we are talking about. And then we calculate rise over run, essentially. I'll show you a couple of methods as we go, of that tangent line. So we're finding the slope of the tangent line, and the tangent line is on that point. So can get a little confusing. We'll go back to trigonometry. So we've looked at sine, cosine, tangent. These two looking triangles should be very, very, very familiar to you after the last unit. This one you might have only seen briefly at the start. So you can see there that tangent, oh, why is that working? Tangent essentially throws the radius out, okay, and then it forms a triangle more on the outside of the circle than what we're used to. Okay, so you can see there the beginnings of a tangent line. So you can make a tangent line by making a triangle on a unit circle, and the tangent one is the line that is fully outside the circle but touching it. So that's kind of where it comes from. But if you don't want to use trigonometry ideas, another way of explaining it is that you want a line where the space on that side is kind of even to the space on that side. So it's not kind of pushing one way or another. Okay, or you can just think tangent line as a line running straight off it. So that tangent line, if we can find the slope of the tangent line, gives us the instantaneous gradient. Okay, we are going to learn differentiation, which tells us the instantaneous rate of change. But to get your head around the concept first, we're going to do a couple of other methods before we get there. So for example, if I wanted to find this instantaneous rate of change at that point, I'm going to give you 2 points. So this one here might be, let's say, 320. And this point here might be 1, 5. Okay, so to start off with, I'll show you exercise sheet so you know what I'm talking about. To start off with, we will give you the tangent line, and we will give you 2 points on the tangent line so that you can find the instantaneous rate of change. As we go along, we won't be giving you the tangent line and we won't be giving you the points, so we'll have to show you some other methods. So this is exactly the same as the linear one we just did. I'm going to make this x2 and y2 and this x1, y1. So my slope is 20 take 5 over 3 take 1, so 15 over 2. So we're looking at 7.5. So at that point there, the graph is growing at a rate of 7.5 units. Okay, so we can take a snapshot and we can do that all the way across. We could find the instantaneous rate of change there. We could find the instantaneous rate of change there. Okay, we can move that all the way along. And I've just grabbed, these are terrible, I'm sorry. I've just grabbed a couple of other examples to show you that with a bit clearer. So the tangent line runs off and we can find the instantaneous rate of change at any point on any graph. Okay, so what I want you to do is go through and do those instantaneous rate of change ones. There's a couple of questions there. And once you've got the hang of that, we're going to go and have a look at a formula and a method that can find those instantaneous rates of change.